In mathematics, a formal power series is a generalization of a polynomial, where the number of terms is allowed to be infinite. This implies giving up the possibility of replacing the variable in the polynomial with an arbitrary number. Thus, a formal power series differs from a polynomial in that it may have infinitely many terms, and differs from a power series, whose variables can take on numerical values. One way to view a formal power series is as an infinite-ordered sequence of numbers. In this case, the powers of the variable are used only to indicate the order of the coefficients. The coefficient of is just the fifth term in the series, while the coefficient of is the 0th term. In combinatorics, formal power series provide representations of numerical sequences and of multisets, and for instance allow concise expressions for recursively defined sequences regardless of whether the recursion can be explicitly solved. This is known as the method of generating functions. More generally, formal power series can include series with any finite number of variables, and with coefficients in an arbitrary ring. Introduction. A formal power series can be loosely thought of as an object that is like a polynomial, but with infinitely many terms. Alternatively, for those familiar with power series, one may think of a formal power series as a power series in which we ignore questions of convergence by not assuming that the variable x denotes any numerical value. For example, consider the series. If we studied this as a power series, its properties would include, for example, that its radius of convergence is 1. However, as a formal power series, we may ignore this completely. All that is relevant is the sequence of coefficients 1, -3, 5, -7, 9, -11. In other words, a formal power series is an object that just records a sequence of coefficients. It is perfectly acceptable to consider a formal power series with the factorials 1, 1, 2, 6, 24, 120, 720, 5040 as coefficients, even though the corresponding power series diverges for any non-zero value of x. Arithmetic on formal power series is carried out by simply pretending that the series are polynomials. For example, if then we add a and b term by term, we can multiply formal power series, again just by treating them as polynomials. Notice that each coefficient in the product tab only depends on a finite number of coefficients of a and b. For example, the x5 term is given by. For this reason, one may multiply formal power series without worrying about the usual questions of absolute, conditional and uniform convergence which arise in dealing with power series in the setting of analysis. Once we have defined multiplication for formal power series, we can define multiplicative inverses as follows. The multiplicative inverse of a formal power series A is a formal power series C such that AC equals 1, provided that such a formal power series exists. It turns out that if A has a multiplicative inverse, it is unique, and we denote it by A-1. Now we can define division of formal power series by defining B, A to be the product bar -1, provided that the inverse of A exists. For example, one can use the definition of multiplication above to verify the familiar formula. An important operation on formal power series is coefficient extraction. In its most basic form, the coefficient extraction operator for a formal power series in one variable extracts the coefficient of xn, and is written e.g. xn, so that x2 equals 5 and x5 equals -11. Other examples include similarly many other operations that are carried out on polynomials can be extended to the formal power series setting. As explained below, the ring of formal power series, the set of all formal power series in X with coefficients in a commutative ring R form another ring that is written R x, and called the ring of formal power series in the variable X over R. Definition of the formal power series ring. One can characterize R x abstractly as the completion of the polynomial ring R x, equipped with a particular metric. This automatically gives Rx the structure of a topological ring. But the general construction of a completion of a metric space is more involved than what is needed here, and would make formal power series seem more complicated than they are. It is possible to describe Rx more explicitly, and define the ring structure and topological structure separately, as follows. Ring structure as a set Rx can be constructed as the set Rn of all infinite sequences of elements of R, indexed by the natural numbers, designating a sequence whose term at index n is in by nn. One defines addition of two such sequences by and multiplication by this type of product is called the Cauchy products of the two sequences of coefficients, and is a sort of discrete convolution. With these operations, Rn becomes a commutative ring with zero element and multiplicative identity. The product is in fact the same one used to define the product of polynomials in one indeterminate, which suggests using a similar notation. One embeds R into Rx by sending an EAR to the sequence and designates the sequence by X, then using the above definitions every sequence with only finitely many non-zero terms can be expressed in terms of these special elements, as these are precisely the polynomials in X. Given this, it is quite natural and convenient to designate a general sequence by the formal expression, even though the latter is not an expression formed by the operations of addition and multiplication defined above. This notational convention allows reformulation the above definitions as in which is quite convenient. But one must be aware of the distinction between formal summation and actual addition. Topological structure having stipulated conventionally that one would like to interpret the right-hand side as a well-defined infinite summation. To that end, a notion of convergence in Rn is defined and a topology on Rn is constructed. There are several equivalent ways to define the desired topology. We may give Rn the product topology, where each copy of R is given the discrete topology. We may give Rn the iadic topology, where I equals is the ideal generated by X, which consists of all sequences whose first term A0 is 0. The desired topology could also be derived from the following metric. The distance between distinct sequences and in Rn is defined to be, where k is the smallest natural number such that at bk, the distance between two equal sequences is of course 0. Informally, two sequences and become closer and closer if and only if more and more of the terms agree exactly. Formally, the sequence of partial sums of some infinite summation converges if for every fixed power of x the coefficient stabilizes. There is a point beyond which all further partial sums have the same coefficient. This is clearly the case for the right-hand side, regardless of the values n. Since inclusion of the term for I equals n gives the last change to the coefficient of xn, it is also obvious that the limit of the sequence of partial sums is equal to the left-hand side. This topological structure, together with the ring operations described above, form a topological ring. This is called the ring of formal power series over R and is denoted by Rx. The topology has the useful property that an infinite summation converges if and only if the sequence of its terms converges to 0, which just means that any fixed power of x occurs in only finitely many terms. The topological structure allows much more flexible use of infinite summations. For instance, the rule for multiplication can be restated simply as since only finitely many terms on the right affect any fixed xn. Infinite products are also defined by the topological structure. It can be seen that an infinite product converges if and only if the sequence of its factors converges to 1. Alternative topologies. The above topology is the finest topology for which always converges as a summation to the formal power series designated by the same expression, and it often suffices to give a meaning to infinite sums and products, or other kinds of limits that one wishes to use to designate particular formal power series. It can, however, happen occasionally that one wishes to use a coarser topology, so that certain expressions become convergent that would otherwise diverge. This applies in particular when the base ring R already comes with a topology other than the discrete one. For instance, if it is also a ring of formal power series. Consider the ring of formal power series Z, X, Y, then the topology of above construction only relates to the indeterminate Y. Since the topology that was put on Z, X, has been replaced by the discrete topology when defining the topology of the whole ring, so converges to the power series suggested, which can be written as, however, the summation would be considered to be divergent, since every term affects the coefficient of Y. This asymmetry disappears if the power series ring in Y is given the product topology where each copy of Z, X, is given its topology as a ring of formal power series rather than the discrete topology. As a consequence, for convergence of a sequence of elements of Z, X, Y, it then suffices that the coefficient of each power of Y converges to a formal power series in X. A weaker condition that's stabilizing entirely, for instance in the second example given here the coefficient of Y converges to, so the whole summation converges to. This way of defining the topology is in fact the standard one for repeated constructions of rings of formal power series, and gives the same topology as one would get by taking formal power series in all indeterminates at once. In the above example that would mean constructing Z, X, Y, and here a sequence converges if and only if the coefficient of every monomial xi yj stabilizes. This topology, which is also the I-adic topology, where I equals is the ideal generated by X and Y, still enjoys the property that a summation converges if and only if its terms tend to zero. The same principle could be used to make other divergent limits converge. For instance in R, X, the limit does not exist, so in particular it does not converge to. This is because for I2 the coefficient of xi does not stabilize as n infinity. It does however converge in the usual topology of R, and in fact to the coefficient of exp. Therefore, if one would give R, X, the product topology of Rn where the topology of R is the usual topology rather than the discrete one, then the above limit would converge to exp. This more permissive approach is not however the standard when considering formal power series, as it would lead to convergence considerations that are as subtle as they are in analysis, while the philosophy of formal power series is on the contrary to make convergence questions as trivial as they can possibly be. With this topology it would not be the case that a summation converges if and only if its terms tend to zero. Universal property. The ring R, X, may be characterized by the following universal property. If S is a commutative associative algebra over R, if I is an ideal of S such that the I-adic topology on S is complete, and if X is an element of I, then there is a unique phi R, X, S with the following properties. Phi is an R algebra homomorphism. Phi is continuous. Phi equals X. Operations on formal power series. One can perform algebraic operations on power series to generate new power series. Besides the ring structure operations defined above, we have the following. Power series raised to powers. If n is a natural number we have where for m1. In the case of formal power series with complex coefficients, the complex powers are well defined at least for series F with constant term equal to 1. In this case, F alpha can be defined either by composition with the binomial series alpha, or by composition with the exponential and the logarithmic series. F alpha equals exp, or as the solution of the differential equation F equals alpha F with constant term 1, the three definitions being equivalent. The rules of calculus beta equals F alpha beta and F alpha G alpha equals alpha easily follow. Inverting series. The series in R, X, is invertible in R, X, if and only if its constant coefficient A0 is invertible in R. This condition is necessary, for the following reason. If we suppose that A has an inverse then the constant term A0 B0 of is the constant term of the identity series, i.e., it is 1. This condition is also sufficient. We may compute the coefficients of the inverse series B via the explicit recursive formula. An important special case is that the geometric series formula is valid in Rx. This says that Kx is a discrete valuation ring with uniformizing parameter x. Dividing series. The computation of a quotient f per gram equals h, assuming the denominator is invertible, can be performed as a product f and the inverter g, or directly equating the coefficients in f equals gh. Extracting coefficients. The coefficient extraction operator applied to a formal power series in X is written and extracts the coefficient of xm, so that composition of series given formal power series 1 may form the composition where the coefficients Cn are determined by expanding out the powers of f. Here the sum is extended over all with k and n, and with a more explicit description of these coefficients is provided by Faa-Bruno's formula, at least in the case where the coefficient ring is a field of characteristic 0. A point here is that this operation is only valid when f has no constant term, so that each Cn depends on only a finite number of coefficients of f and g. In other words, the series for G converges in the topology of Rx. Example: assume that the ring R has characteristic 0. If we denote by exp the formal power series, then the expression makes perfect sense as a formal power series. However, the statement is not a valid application of the composition operation for formal power series. Rather, it is confusing the notions of convergence in Rx and convergence in R. Indeed, the ring R may not even contain any number E with the appropriate properties. Composition inverse. Whenever a formal series has f0 equals 0 and f1 being an invertible element of R, there exists a series that is the composition inverse of, meaning that composing with gives the series representing the identity function. The coefficients of may be found recursively by using the above formula for the coefficients of a composition, equating them with those of the composition identity x. In the case when the coefficient ring is a field of characteristic 0, the Lagrange inversion formula provides a powerful tool to compute the coefficients of G, as well as the coefficients of the powers of G. Formal differentiation of series. Given a formal power series in Rx, we define its formal derivative, denoted df or f, by the symbol d, is called the formal differentiation operator. The motivation behind this definition is that it simply mimics term-by-term differentiation of a polynomial. This operation is R-linear for any a, b in R and any f, g in Rx. Additionally, the formal derivative has many of the properties of the usual derivative of calculus. For example, the product rule is valid, and the chain rule works as well, whenever the appropriate compositions of series are defined. Thus, in these respects, formal power series behave like Taylor series. Indeed, for the f defined above, we find that where dk denotes the kth formal derivative properties, algebraic properties of the formal power series ring Rx is an associative algebra over R which contains the ring Rx of polynomials over R. The polynomials correspond to the sequences which end in zeros. The Jacobson radical of Rx is the ideal generated by X and the Jacobson radical of R. This is implied by the element invertibility criterion discussed above. The maximal ideals of Rx all arise from those in R in the following manner. An ideal M of Rx is maximal if and only if MR is a maximal ideal of R and M is generated as an ideal by X and MR. Several algebraic properties of R are inherited by Rx. If R is a local ring, then so is Rx. If R is Noetherian, then so is Rx. This is a version of the Hilbert basis theorem. If R is an integral domain, then so is Rx. If R equals K as a field, then Kx is a discrete valuation ring. Topological properties of the formal power series ring. The metric space is complete. The ring Rx is compact if and only if R is finite. This follows from Tikhonov's theorem and the characterization of the topology on R(X) as a product topology. Applications. Formal power series can be used to solve recurrences occurring in number theory and combinatorics. For an example involving finding a closed-form expression for the Fibonacci numbers, see the article on examples of generating functions. One can use formal power series to prove several relations familiar from analysis in a purely algebraic setting. Consider for instance the following elements of Q(X). Then one can show that the last one being valid in the ring Q(X, Y). For Ka field, the ring K, X1, XR, is often used as the standard, most general, complete local ring over K in algebra, interpreting formal power series as functions. In mathematical analysis, every convergent power series defines a function with values in the real or complex numbers. Formal power series can also be interpreted as functions, but one has to be careful with the domain and codomain. If f equals an xn is an element of R(X), S is a commutative associative algebra over R. I is an ideal in S such that the I-adic topology on S is complete, and X is an element of I. Then we can define this latter series is guaranteed to converge in S given the above assumptions on X. Furthermore, we have an unlike in the case of bona fide functions. These formulas are not definitions but have to be proved. Since the topology on R(X) is the adic topology and R(X) is complete, we can in particular apply power series to other power series, provided that the arguments don't have constant coefficients. F and f-1 are all well-defined for any formal power series f(R)(X). With this formalism, we can give an explicit formula for the multiplicative inverse of a power series f whose constant coefficient or equals f is invertible in R. If the formal power series G with G equals 0 is given implicitly by the equation f equals x where f is a known power series with f equals 0, then the coefficients of G can be explicitly computed using the Lagrange inversion formula.